Ground control to Major Tom. Ground control to Major Tom. Take your protein pills and put your helmet on. Ground control to Major Tom. 8, 7, 6. Commencing countdown, engines on. 3, 2. Check ignition and may God's love be with
Are we good to go? We're good to go. Good afternoon, everyone. Welcome to the Kongshøll and welcome to this event today, hosted by Fróðskaparsetur Føroya, the University of the Faroe Islands. And I'm here today to present David to you. But before I do that, I just want to say a few words about our university and how happy we are to have David here today, if I'm pronouncing your name properly. Is that right? Yeah. How happy we are to have him here today because of the way his work fits in really well with a message that we have about the role of the university here in the Faroe Islands. So first of all, let me introduce myself to, I don't think I've met many of you before, met some of you before, but my name's Chick Collins. As you can probably tell, I'm not from the Faroe Islands. I'm from Scotland. I've been here on the Faroe Islands since September 2019, when I became the rector of Fróðskaparsetur Føroya. Someone sent me a job advert for the position of rector here at the university, and they sent it to me initially as a joke. They know that I'm a football supporter, and I support not a very good football team. And they said, Chick, this is a job that you should apply for, because if your team ever gets a chance to play in Europe, this is probably as far as you will ever get to travel, to the Faroe Islands. So they meant it as a joke for me, but I didn't see it or treat it as a joke. When I looked into the story of the University of the Faroe Islands, I found a story which I thought was incredibly inspiring, of how a small nation of 52,000 people creates a functioning, modern, recognizable university with 5 faculties and the central administration, which performs an absolutely essential role in educating people in the Faroe Islands and developing research which is important to Faroese society, economically, socially, and culturally. So I didn't find a joke, I found a story that I thought was very inspiring. And I thought that if I came here to the university, I could help to develop that inspiring story into a new future in 2 main kinds of ways. First of all, by supporting our university to do basic things really well. But also, in the longer term, to help to have a discussion with all of the relevant parties in the Faroe Islands about the kind of university that we can have in the future and how it can serve the needs and the purposes of the Faroe Islands in the future. So that is something that we're very keen to do, and as part of that work, we believe that we need to reach out, we need to engage with organisations here in the Faroe Islands, whether those are public sector organisations, private sector organisations, voluntary organisations. And we need to have a deep discussion about visions of the future and the ways that we can collaborate to bring that vision of the future into being in the present. And it's wonderful, actually, I think, to be able to bring David into that discussion, because when we're talking about inspiration, I think that he is a wonderful person to have here to talk to us about both inspiration and collaboration. So this inspiring vision of this incredible technology on a remote planet, beaming pictures and knowledge back to us, and you speaking today about the search for previous life on Mars. What an inspiring vision. And I don't know, maybe you can tell me, David, how many people have collaborated to bring this vision into being?
Oh, that's a lot.
That's a lot.
10,000?
It's okay. Tens of thousands of people have been necessary to bring that into being. It's not the product of 1 or 2 people having an idea. Well, to some extent, it probably is the product of 1 or 2 people having an idea, but then many people collaborating to bring that vision into being and to realize it as an actually existing thing, not only in this world, yeah, but in another world altogether. So, this discussion has come today, or this presentation has come today, out of an initial discussion that we have been having with a very important Faroese organisation, which is Føroya. We want to collaborate with them. We want to work together with them to think about future technologies, to think about communication technologies, to talk about satellite technology, and the place that the Faroe Islands in the future can have in the development of that type of technology. To some people, that may seem somehow beyond what a population of 52,000 people is capable of doing. But actually, most people I talk to think that a modern functioning university is beyond what 52,000 people are capable of achieving. So in some ways, you know, the stars are the limit for what we believe that we can achieve together here on the Faroe Islands through the university. And so it's my great pleasure today to present David to you. He will tell you about his work. I'm a social scientist. I can't begin to talk about the work that David has been doing. So I would just ask you now to put your hands together to welcome David, and I'm sure we're all really going to enjoy his presentation. Thank you for being here today, David.
Thank you very much for that very nice introduction. Thank you for Setre and for FT to host this afternoon. Thank you for having me. I'm very delighted to be here and present this work for you guys. I'll be going through some of the technical stuff, some of the scientific stuff, and just bring everything a bit down to earth and at a high level, so we get an idea what this is all about. First off, I shall time my time here. We're talking about an instrument on a rover. It's called PIXL. That stands for Planetary Instrument for X-ray lithochemistry. And I'm sure that doesn't inform you guys at all. But I'll get to that, what it actually means. But it's built for a specific task of detecting biosignatures, whether it's on Mars, Venus, on Earth, it does not matter. It's the same process and technique that's being performed. But this specific instrument is dedicated for the operations on Mars. So in the past, on a scale of, what's that in English? Miljarder, miljardi. So that's billions, right, in English. For about 3 billion years ago, the conditions on Mars and Earth were very, very similar. They are not today. Today, Mars has no magnetic field. That means that it does not have a liquid core inside the core of the planet. Once it loses the magnetic field, the solar wind will kind of blast away the atmosphere, so it cannot contain liquid water anymore. So that's why it looks like it does. But for 3 billion years ago, they did have the same environment. So we did have a magnetic field on Mars, and we did have liquid water all over. We had large oceans on Mars. So this kind of ripples to the missions that we have had so far. They kind of were exploring the habitability and the water content on Mars, and that has been proven over and over again by orbiters and other rovers that there is ice on Mars. It's frozen form. So it kind of moves into another era where we're looking for biosignatures. That means signs of past life in forms of fossils embedded into rocks. These fossils are very similar to those that we have here on Earth, and also from the age of 3 billion years ago. And that's why we think that if we're going to look for signs of life on Mars, it's in a fossilized bacteria form, because with that content we have seen here on Earth too. I'll get more into that. But for this mission here, we have 4 main objectives. That's the habitability and biosignatures that you see in the first on the top left corner. We have the geologic exploration of the environment. We are preparing for a human exploration for the future. I mean, we have some technology demonstrators. You know, the helicopter, for instance, or the one instrument that's preparing for human exploration in the future. And we're also preparing for a returnable cache. What does that mean? That means that we are preparing for a return of a sample of Martian soil to Earth. That, to me, that still seems like a science fiction type, but it actually isn't. It's very much in the making. That is actually done by this rover Perseverance going around and sampling these samples. They are the size of about a finger. It will drill these out and put them in a container, drop them underground, and leave them there. So there are pretty much room for around 30 or something samples. Once that is done, another rover will come by, pick these up, store them in a container, a bundled container, and load these up to another rocket that's been landing. It's probably going to be around 2 meters high, this rocket. It will only have fuel to get into orbit of Mars. Once that is done, God help me, a third mission, a orbiter will rendezvous with these samples in orbit of Mars, capture these, and bring them back to Earth safely. So this is there are 3 parts of that mission, but it's very much it's far beyond the drawing board. The proposals are called for. That means that NASA and ESA are calling the industry and universities for solving tasks to bid for these tasks and provide hardware and solutions for it. So this is probably 10 years from now that we'll get these in hand on Earth. Now the Perseverance rover has how many is that? 7 main payload instruments. The 2 top ones, that's Mastcam-C and SuperCam, they are mounted on the mast and will kind of explore the geology and the rocks from a distance. We have Pixel and Sherlock that are sitting at the end of the robotic arm. These will explore the soil at a very, very close distance, around 3 centimeters. We have MOXIE, which is a technology demonstrator, which actually it will produce oxygen from CO2 from the atmosphere of Mars at a very small scale, but it will demonstrate it can perform in these environments. And once that is done, we can scale that up to provide oxygen for a habitat on Mars or for fuel for a rocket to lift off again. We have MEDA. MEDA is it's kind of a bundle of instruments that's exploring the atmospheric conditions on Mars, the wind and stuff like that. If you heard the sound bite from the wind on Mars, that's from MEDA. And we have RIMFAX, that's a Norwegian instrument. That's a radar, ground-penetrating radar. I think it goes down to around 2 or 3 meters to explore what's underneath. So the mission lifetime is 1 Martian year. That's 2 years here on Earth. Make no doubt about it, I think we are gonna operate much, much longer than that. Ballpark, say 15 years at least. And we had launch in August last year, and we landed here just 18th of February this year. Okay, so the scientific objectives of the Pixel instrument, that is mainly to look at the biosignatures if we're lucky to find it. but otherwise, we are also a part of just exploring the soils at a very close distance. And you can, to put it in context, we have orbiters that are flying around Mars and the planet, and they can investigate the surface from a distance at a larger scale. And then we have the mast instruments, the Mastcam C, for instance, and Supercam. They will explore the outcrop scale if you just look at it with your bare eyes. But as a geologist or astrobiologist, when you're looking into this, the next big thing, or the next thing that you do naturally, if you're in the valley and you look at something interesting, you pick up your forstørrelsesglas. What's that in English? Magnifier. Thank you. That's good. You pick your magnifier up from your pocket and you start to explore it at a more detail, right? And once you do that, you think this is kind of interesting, and you think this is a good candidate for a biosignature or something. Then you pick it up and you bring it back home for further investigations. So Pixel fits in to the magnifier scale to actually locate a good candidate for this. It all started with this astrobiologist and geologist Abigail Allwood. She's actually a researcher from Australia that has the record of finding the oldest fossil on Earth, which is 3.4 billion years old. And she teamed up with this amazing guy, Larry Wade, who's very, very good at building instruments and designing them. And they put a larger team together to put a proposal for an instrument for this rover, and they won. I mean, usually you have to have 3 shots before you actually you win the assignment, but they won it from the first go. So these, together with a larger, broader team, are actually the ones with the idea behind it. Pixel works by, the main element of Pixel is the X-ray lithochemistry and fluorescence. What happens is that it has an X-ray source and will shoot out a very, very narrow beam of X-rays. They are so narrow that they are focused to a beam of the thickness of a hair. And that's important, as I'll show you later on, that we can scan the surface instead of just looking at a bulked spectra. But once the material is hit by an X-ray, it will fluoresce back a specific signature depending on what the content is. I mean, so iron will have a peak and at a specific energy level, and titanium will have another peak at another place in the energy spectrum, aluminum, silica, you name it. And that's how you actually detect what's in the soil of the surface. So as I mentioned, we're actually doing scans of this, but we need to correlate these measurements to the visual aspects and to the texture of the surface. Because you see on the top right there, that is a very keen candidate for a biosignature. But if you just look at the X-ray spectra by itself, it does not tell much. But if you correlate it to this visual features and specifically the map of it, you see on the lower right side, you see a map of some of the elements, vanadium, silica. What else do we have? Iron. And one of the elements is that you don't have any iron in the centric of it. And that's typically one of the signatures that we have of a biosignature. There are quite a lot of these, and I'm by all means no expert in detecting biosignatures. I build instruments. So of course I'm a part of a larger team that have these experts in hand. For instance, Abigail Allwood, and that's what this is all about. These biosignatures are typically found in shallow water. For instance, we take the Great Bahama Bank, or we could take some. You see, it's just outside the Florida coast, the coast of Florida. We also find them a lot in Australia. And what we're looking for is these stromatolites, fossilized stromatolites. It's mats of bacteria that's just been growing and growing and growing, a layer on top of each other. And once these fossilize, they kind of leave traces or clues that we can look for in order to say whether these striations are formed from a geological process, which happens all the time, or it's from biological process. For instance, that we see some of the iron-rich dolomite cavity linings within the cement, and these are typical for a biosignature or a biological process. So I'll move just a bit further on the technical side. We had the initial proposal in 2014, and it looks quite rudimentary compared to the final instrument. But all the main elements are there. We have an X-ray source, we have an X-ray detector, we have a camera for context, we have some light or in form of LEDs, but it did not really cope with the constraints that NASA has. So we took an iteration back on the design and put some other additional elements on it, and it got accepted. But as time goes and you start build and design, you learn more, and we found out that we need another iteration of the design. So in 2016, you can see some of the footing elements. So that's actually a hexapod of 6 linear actuators that can move the instrument about. We have now 2 lasers embedded into that too, because we found out that we need to know the distance towards the surface in order to maintain a proper focus of the X-ray. It will collimate and will diverge again if we move too far from it. So we have a narrow window where we are having optimal performance, and we need that. I'll show you later on an example of how that is actually done, that navigation. This is the final version. We see here, this is where the instrument is being tested in the facility of the Jet Propulsion Laboratory in Los Angeles. That's a NASA institution. We have floodlight electronics, X-ray optics, dust cover, you name it. That's quite a lot of elements in there. And I think in the interest of time, we don't have time to cover everything. But just to give you a feel for the size of it, this is one of the prototypes from of the front cover you see there. This is just 3D printed titanium, and it had to have this be 3D printed in order to save weight and have the strength that we need for it. We have the camera housing. This the size of it. It's very, very light. It's around 100 grams or so. We had to literally fight for each gram that we had on board for this instrument. And later on, from the landing, I was kind of surprised at seeing that the cruise stage was dumping around 100 kilo of balance weight, and we were there fighting for every single gram. That was a bit, I don't know, surprising to those in the fight. But and then we have a computer unit That's this part here. This is a standard computer for spacecraft use. That's a remnant from the star tracker that's built and manufactured at DTU Space for quite some years. It has heritage from I think the first one was built in '96 for the Ørsted satellite, and it's flying now for just around 100 missions so far. And the thing is that it usually operates for a star tracker, so the thing is that we only change the optics on the front end and the housing of it in order to fit into the instrument volume envelope. You see that both elements are covered in gold, and that's 24 karat gold, and there's a reason for that. It's because of all the electronics in the body of the rover. We need some method to control the heat, the temperature environment in that body. And if you have a failure mechanism for one unit, we need to make sure that it does not have a runaway situation where everything else is just self-heating also, and then the mission is lost. So with a cover of gold, it has this capability of not leading the heat away. So it's kind of self-contained to that instrument. If it gets hotter, it does not give the heat further on. So that's a kind of a passive control design to control the thermal environment on the body. These are some of the units, or actually all of the units that were delivered by DTU. We have the camera end, and we have some electronics on the lower left side. That's just a bank of energy storage of capacitors that are ready to flash the floodlight unit. Floodlight unit, that's essentially just a blitz or flash, if you will, so we can operate during the night. We have some lasers also. Those were actually built by JPL, and we had the computer that's just mounted as a piggyback on the bigger instrument computer. So coming from a star tracker, how is this relevant for surface ops? I mean, we're usually looking at stars and navigating by use of stars, and I mean, how does this relate? But if we have a sample here where we look at the surface of a rock and we illuminate it with one laser dot, how a machine will be very bad at isolating that laser dot that we'll be using to navigate the instrument. But if we take a reference image with the laser off, we can subtract the two images very, very simply, and it looks like there's no light in it, but we are able to isolate the signature from the laser only. So we get rid of all of the other stuff, and we can detect these spots. But now we're not going to settle with one spot. We have two lasers, so one will be dense, one will be sparse, looking at the wider area. And how to actually separate the ones? How do we know which one's which? Because this could just be a sample from 15 dots from a normal surface. You can't really see which one's which. But it happens that the lasers have a linear trajectory in 3D space, and if we can calibrate that, we can map that onto the field of view of the camera, and they will always be there. They will always follow that trajectory regardless of the distance. And so using that, we'll be able to isolate and uniquely identify which spot is which, and actually use that to triangulate onto the surface and determine a 3D distance from the instrument. We have two types of lasers, one for dense area with a grid of 3 by 5. That's designed to be surrounding where the X-ray beam is incident on the surface. The other one is designed for a safe approach, so having a wider coverage, We don't want the instrument to be bumping into the surface at the first go, so we're always keeping track of the distance as we go closer. This is one of the additional ones. We are usually looking at planetary objects on a dark background, and fitting these to a circular shape, and we can navigate using these heavenly bodies. But of course, we can also use these to track circular abraded cores on the surface. It happens that it has an abrading tool, to expose the inner surface of the rocks, and so we're not just looking at the weathered surface. And by that, we can use it to position ourselves directly over the center of the abraded surface, and save a day of operation, in order to not to iterate on that position all the time. We also need, this is actually even more important, because a scan for this instrument, a full map scan takes around 10 hours. And on Mars, we have a thermal change from around 20 degrees Celsius to minus 80 degrees Celsius from night to day. And you can probably imagine that nothing is really stable over such a wide thermal envelope. Everything contracts as the temperature degrades, and you can also say that, are we really sure that the ground beneath where the rover stands is that stable? I mean, you can imagine sinking a little bit as the temperature decreases and rises. So we have these algorithms to detect features directly on the surface of the that we're looking at, and can use those to position ourselves very, very accurately. And that's partly why the guys at JPL at NASA say that it's one of the most advanced instruments on a rover, because it takes completely over all the control, all the navigation parts. That's usually done in a larger scale, but the instrument does everything by itself. We're pretty much placed by the rover initially, then we take over everything, because none of the other actuators on board can give us an accuracy that will be able to scan the surface at a scale of 100 micrometers. And I said partly, this is also one of the elements that is doing it. This is the hexapod, developed by JPL at NASA. It will allow us, it has these 6 linear actuators, and these will allow us to navigate and pivot the instrument and position it as we want it, very, very accurately. You could think of other constructions, but a typical construction like a hexapod is very, very accurate to some few microns, so a factor of 10 better than what our requirement is. This here shows you an animation of a scan. You see the green dots, that's where the X-ray actually intersects the surface. You see the blue frame, that's the area that the camera sees, and you see these red and purple dots, that's the structured light illuminators, these laser lights that illuminate the surface for navigation purposes. And it does this grid scan all the way through, full grid, 10 hours. We are also capable of doing some just linear scans or lines, and will take half an hour, 1 hour-ish. Depending what we want from the specific sample that we're looking at. One of the reasons, pretty much the reason why Pixel won the proposal is that it's able to ability to resolve the features. We can see cracks, and we can see white spots, dark spots, and we can't really see what they are if we have a a average beam that's on this size scale, that's around 1 to 2 centimeter in diameter size. So having a finger size measurement that just picks up the spectra or the elements on an average scale for all that sample, that's not going to give us the details that we're after. And if you look at this is a typical XRF or X-ray fluorescence instrument that the field of view that it has. And if we look at the former generations for instruments on the other rovers, it gets even worse. So what can you do? You can use pixels to make a scan of the surface. And that's why it's important to have this narrow beam of X-rays that are incident on the surface, so we can actually get the details that we're after. One element more is that we have, this is actually one of my favorite pictures, because this is where the rover was being assembled at the High Bay facility. I can't really see, where is that computer? I'm pretty sure it's installed at this point in time. I have no idea where to look at it from all these cables that are in here. I don't think I'm lying if I say that NASA's problems, it's typically 90% of it is cables. Funny enough, but I mean, usually when we deliver instruments, we deliver it with a computer, with a cable to the optical head itself, so we can test out these elements in a final flight configuration. But with a rover like this and a complex machine, it has some flat flex cables out to the rover's arm. Typically what you see in a laptop or something like that. But they have a certain characteristics, and we always need to fine-tune our instrument to the specific cable that we have. And if we're not very, very careful, we can forget that when we mount this at the I forgot to say that when we delivered this instrument, it was delivered in 2 parts. We did not have any design or control over the cable. That was on their side, and then it was not tested in final configuration until it was completely assembled. And if we're not very, very careful at that installment, and you test it in an environmental chamber, a thermal and vacuum chamber, you can see funny things. We had an experiencing that the imager was not working properly at very, very cold temperatures, and we got a call from NASA and said, well, what is going on here? You need to resolve this right away. Of course we do. We jumped on the horse and tried to figure out what it was. Came down to a simple test that was supposed to be done during the installment. It takes half an hour to do, and then we have the right setting for the communication. But it took us probably 14 days to figure out, and 4 months to convince NASA to that was actually the root cause. So it pays off to pay attention to details at an early stage. This is a picture from the integration and the calibration. We're just calibrating all the instruments, so we know how many cameras. There's 30 cameras that are on this machine, both navigation-wise and instruments scientific-wise, and they all need to be calibrated relating to each other. Once it's tested and calibrated, it will be installed into the cruise stage. You see the heat shield in the bottom. You see the rover with its wheel assembly being pulled up in a crouch stage, if you will. And you have the cruise stage on top with the solar panels and the propulsion tanks. Once that is tested and integrated, you put it into a fairing. Fairing is the top, the business end of a rocket, if you will. it's fairly large, isn't it, compared to the payload that we're actually launching. But we needed that much velocity to get out into Mars, and this was the only fairing that was able to cope with that acoustic and vibration load that's actually on the from the rocket. So they do have smaller fairings, but this was the only one that could cope with it. And then you mount it on a rocket. I tried to show with the scale of the images, the scale of the rover compared to the rocket, and you can probably pretty much see that how much of equipment is built just to get it into orbit, and how much fuel is actually burned off. So this is quite a task to get everything done. And the team was coping with the COVID at the time, and everything was shutting down, and they had teams working, isolated from all the from the rest of the world, just to keep a bubble, if you will. And they did very, very well. Launched on the 30th of August last year, and then we're going to fast forward to this short video just showing this is actually showing, I'm guessing that some of you probably, if you follow the landing itself, you could see a lot of animations going on, how it landed, and all the steps that it had to go through with the parachute, with the drop of the heat shield and all that jazz, and the sky crane. But this one shows the actual footage that's captured from that series, from the actual stages that came down some 3 to 4 days later. These are actually the first footage we have from this sequence. We didn't have it for Curiosity. So yeah, let's take a look at this. Mr. Sound on it there?
Jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Applicant indicates chute deployed.
The navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
Heat shield set.
Perseverance is now slowed to subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
We'll start to see some of the edge of the crater on the top right side. And
Net filter converge. Velocity solution 3.3 meters per second. Altitude 7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers above the surface.
And that's a critical side of it, that we don't want to land too close to the crater.
Parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
So you will see that it will start dropping the sky crane itself.
Oh, yes, valid.
We
have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
Priming. TBA is nominal.
We have priming of the landing engines.
Back shell set.
Current velocity
There you
is
go.
83 meters per second at about 2.6 kilometers from the surface of Mars.
And you see
There's
that it's
confirmation that the
tilting
back shell
just
has
slightly.
separated.
And that's essentially
We are
to get
currently
away from the
performing
critical
divert
side.
maneuver.
And
Current
it will start to
velocity is about
overshoot a
75
bit
meters per
and
second
find
at
its
an
way back
altitude
afterwards.
of about a kilometer off the surface of Mars.
TRN safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver. Sky crane maneuver has started, about 20 meters off the surface.
We're getting signals from MRO.
Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
You see that they're quite cheerful because they say this was the most critical part of the whole mission. A launch is typically not that critical, at least for a rover, because that's compared to a landing, it's done all the time. Landing like this is done twice now. Well, they have a good percentage coverage. They've done it successfully 100% of the time, right? But a launch is done on an almost daily basis compared to a landing. So where did we land? We have the Vestaru crater. It's believed to be a water basin. It's a crater from major impact, and we have it's just filled with a shallow water basin. And you see on the left side, if you can see it, there's a dark circle that's just highlighting the landing zone, landing ellipse. That's the accuracy that we expect to land in. And you see that the high footage from HiRISE, that's from MRO, the Mars Reconnaissance Orbiter, one of their instruments that we see on the right side. We can see Perseverance on the bottom side. We see the descent stage. We see the parachute and back shell, and we see the heat shell also just dropping right directly down. So this is our landing site. And what happens after that? We have a commissioning time of 3 months, a bit to the long side, but that's because we have some elements on for a helicopter drone that we want to test out at the first stage of the mission. We had so a sol, that's a Martian day, just to be if you're not on that. So we used 5 days, Martian days, to just check the aliveness of the instruments and the rover itself. I mean, can we fire up the computers, the motors, the drive change of the wheels and stuff like that. We transitioned to a flight software. You update software all the time, right? So we can also do that on a rover. We further checked out the instruments, and we start to begin mobility. And this image here, one of the favorite ones, you see pics on the left side. So we're looking with the mast directly ahead, and you can probably see that we actually made a donut, looks like. But on the top left and right corners, you can see that kind of a brighter area, and that's where the jet engines were hitting the surface and kind of cleared way of all the dust on the surface. We had a checkout for the robotic arm, which Pixel is mounted on. Did some maneuvers of that, and now we are into testing of the technology demonstrator Ingenuity, which is a helicopter drone that will be flying in the atmosphere of Mars. It has dropped it from the belly of the rover, of beneath the rover, and it will start its initial flight in 3 days' time or something like that. After that, we have a 30-day of payload calibration and validation. That means that our instruments will start to look at their calibration targets, and will make sure that the calibrations done on ground actually correspond to those that we have in flight. After that, it's straight on to scientific observations and the science shift. These were actually one of the first results from our instrument. It kind of looks weird because we at that time we haven't opened the front cover at that time, so we're just looking at the inside of the cover, and you see on the right and left side of the image these bright spots. That's the lasers being illuminated. They are not in focus because it's very, very close. So if you open the front cover, you'll see that it has this nice pattern that we designed for. And on the right side, you see the X-ray spectra coming back, and the nice thing about this is that we have no detection of dust at all. So we just see some silica and calcium and zinc and nickel, and that's all part of the paint of the inside of the instrument. Hooray for the dust cover! That actually works. So next up, we're gonna fly the instrument, the rover itself. The drone. That's a technology demonstrator. It has these goals of of actually lifting off and just landing directly again, lifting off a bit higher, and then actually flying some 100 meters along the surface. And that's pretty much it, actually, that we expect to have out from it. But if this can be proven to be working, we can actually use these in the future for other missions. That we can use these as scouts, for instance, or we can, get ahead of above the hill on the other side to see what's actually there, so we don't have to spend days or weeks driving there and seeing, there was nothing interesting anyway, because we want to use our time on the surface of Mars rightly, because it's also in terms of money. A project like this, if you narrow everything in, what does a day on Mars cost? And that's typically in the order of 28 million kroners. So you need to spend it wisely. You don't want to spend time just driving around looking for stuff that you don't have success with. Finally, I want to give credits to the team at the DTU Space. We are some 40 people that have been working on this project. I am a measly part of the whole project. I think for the Pixel instrument, there were at least 800 engineers throughout the years. So you can scale that up if we have 7 of instruments, and then we have the whole spacecraft itself. So that's why I say 10,000 people working on this project is not too far of a bit. These guys work very, very diligently, and we need to cover a range of aspects, and we all rely on each other. I have an expertise in my research field, which is navigating using imagery, but then I rely, of course, on other people that can build design the electronics, that they can design the mechanics, that are very good at testing the equipment. All of this has to work together, and we need to test out components and stuff like that. It's a very, very wide field within the spacecraft industry. So with that, I will say thank you for listening, and I hope you enjoyed. I should probably ask or anything like that.
We have time for questions.
Yeah?
Yep. So, wonderful presentation, everyone. I'm sure everyone enjoyed it very much. We have a wide range of people here today. I'm particularly glad to see some younger people here today, maybe the scientists and technologists of the future, and their ranks here today being inspired by David. So, David has some time for some questions, and I hope we will make some very good use of that time. So, who will begin?
Ja, det er allerlei. Ja.
Environment usually counts you deal with extremely harsh environments. So if you think about designing challenges such as cabling, insulation, potting of electronics, most materials become rather brittle when you go down to really low temperatures. How much does that factor in your typical design?
A lot.
Yes.
Extremely much. So the question is, how do we cope with the environment being so extreme? And it varies from mission to mission. Some missions for Jupiter, for instance, we have extremely much radiation. So we have a vault simply for all the instruments to protect it from radiation. There's not that much radiation on the surface of Mars, but the temperature plays a big role. Typically, you can isolate or thermally control a spacecraft so you have a stable temperature throughout the mission, typically at 0 degrees or minus 10 degrees. But for this, you're in the environment. You need to cope with it somehow. So there are for some parts there are heaters on board. For instance, the helicopter drone, it just has a battery. We all know batteries don't last that good at minus 80 C. Just take your phone outside in this cold and you see your energy storage just drops quite significantly. So it has a heater for the battery. But when we design for missions like this, we need to take into account all the environments. I mean, just for a printed circuit board, for the electronics, we need to make sure that the thermal expansion of that board actually corresponds to the thermal expansion of each single component. Because if it does not match, I mean, say the board has a larger thermal expansion to the component, the soldering of the component will just crack and it will lose connection, and that's not good. So there is extremely high attention to those details. And every time you build a printed circuit board, you have, not only when you design it first time, for each single one that you build and deliver, you have an inspector from either ESA or NASA to come by and inspect it, look into a microscope and investigate whether the soldering is to the quality that we need, and if it's if it is expected. Then there's the question of components. That's the capacitors, the resistors, the transistors, all the electrical components that we have. You can buy them off the shelves, so they're cheap, but you can also buy them very expensively if you have the manufacturer specify that it can be rated to a higher range of environmental thermal environment. So it can cope with a lower degree of the temperature, for instance. But those are very, very expensive. So we have we have, how many are we? 5 of these guys are working in a group where they only work on the components and test them for radiation, thermal resistance, and or the expansion. If there's water, it's starting to creak into the cracks of transistors, stuff like that. Cutting them, looking into their in a microscope, looking into their intestines, so to say. Very, very diligently, and you need to make a report of all the components that you have, that you specify how it tolerated the specs, and if it does not, you have to discard it. NASA and ESA, they are good at this too, of course, so they always keep up with their experience in flight. And they see, not too many years ago, they saw that the water was creaking into the cracks or creeping into transistors. And nobody was testing for that. And that was one failure mechanism for our satellite. And now everybody tests for that. But then everybody loses, 25% of their components that you have available for storage or for use. And so they need to come up with 25 more, So it's an ongoing, never-ending process, and it's a big deal of it, yeah, big part of it.
Yep.
Very good question. So the question is whether we have private actors involved, or is it just universities or bigger agencies? We use a lot of manufacturers. We try to use Danish contractors, so we keep, so we support the local business, right? All the optics that we use for all missions, that's made by a Danish company in Copenhagen, and they cut all the lenses and polish them and stuff like that. We try to use printed manufacturers or Danish manufacturers for printed circuit boards, but recently we had to change to an English or American manufacturer. But we definitely rely on private actors all the time, because it has to be delivered somehow. We cannot make everything by ourselves. So absolutely. But you also see SpaceX is also a private business, but they are contractors to NASA, right? So NASA is partly, it has its own agencies and its own people to build stuff, but usually they contract it or outsource it. So they get it built outside, and then they assemble everything for the full spacecraft. And we, as a university, we can bid on a assignment just as every other agency can, or every other university or private actor can. That's perfectly allowable, so there's no hindering there.
So you basically bid on Pixel
Yeah.
at a level playing field with any other, for example, private contractor? Or just
Yes. So there we kind of had an assembled team, but that was the Abigail Allwood from Australia, Larry Wade and the team at NASA, and we had some from a private company in Chicago. I think they actually built the tube for the X-ray, because this one of the best guys in the world for X-rays tubes. He works in Chicago, and that's where you want to go if you want the best one. So you bring in people that have the right expertise, and you a part of that, bring in the people. You also get in manufacturers or to build the equipment itself. So we kind of build a bit on the assignment as a whole team, if you will.
Jeg har en spurning faktisk selv av Føroyski.
Ja.
Kikk tar seg at det deilt å søke til ung, og jeg er Brynhild Thomsen i arbeid av Setrum og Neisene. Jeg har ikke opplevd før at fyrilestrar og i Kongshøll vi tror av akademikere for foreldre ringer inn og sier unga billetter etter til bøttene. Ja. Men det har vi opplevd i det. Jenter og eisene en dronker som ikke slapp tegna seg, men jeg håper det er kommende likevel. Kan du komme ved noen gåen ravn til bøtten og ung som fyller brennende vi, hva hender ut i mars og hittar etter det her, og to hever eisene ginger i Havnagøten og ginger i skole her og så. Kan du gjøre noen gåen ravn? Hvordan kommer man så lengt fra noen av skolen ut av mars, eller hva man skal si?
Ja, altså, det er jo gode spørninger, og jeg kan bare si det fra munnen, hvordan jeg har opplevd det. Altså, jeg må si det som det at komme opp på en sånn misjon her, til eisende et element av held. Altså, sjån det krever til at man vi haldande og arbeider nekk for pata, men man skal eisende hele tiden å komme inn i prosjektet til akkurat rette tidspunkten. Altså, så er det eisen i vysen av verden, at til eisen det rette tidspunkt timing, hvordan kjenner man ikke, men den største parten er sånn det at man arbeider kjøttene i pata. Og altså, i tirsdag jeg har en idé om at jeg skulle arbeide hvis det var helt ung. Anskjanser, altså. Jeg halte altså, jeg minnes da, jeg har gitt til nannskolen og kommunskolen, Og kommunskagaren her I Chattlaren här var ett litet laboratorium vi kan sitta och lotta och göra sin elektronik och liksom för ut och idéer och kanske spela ett sånt vitt att det är det här som man lär vi det är att spela sånt det är nu vi händer legend vad hänt så alltså vi nu säger heter så lyser lampan alltså och det är förvittne som för medrövda och alltså är väl egentligen helst för rockmusiker spela gitarr och du vet men alltid måste på en touch måste inrymma liksom att det blir ju ordentligt bättre än det så kanske så finna på andra och så hur säger jag men okej men kanske kan jag förstärka till gitarr eller short och så skulle jag mena DTU Elektriska universitetet och jag vet också när vi iva om alltså från det ska det vara mer efter digital elektronik ska det vara software ska alltså kvar ska analog elektronik alltså kvar specifika lag ska man ta och det var faktiskt för en början om en kandidat att ett tog fag DTU Space vi som är introduktion till satellistsystem ta checkt upp för mig att så kan de arbeta visst ner alltså är det något som arbetar till förväg i Danmark alltså så jag var så hutigen att jag tog ett kursen jag kunde vi bara runt där och så kvarta var det var faktiskt rätt lugga mycket om det var mekanik om det var regulering om det var alltså algoritmer till det här bruk och jag fann så där att en avdelning av DTU Space som levererar nekva hardware och därför är vi värden till att leverera navigationstol och magnetometer och så fräckras på hur vi skulle arbeta vi är till time att man kan ta så alltså det är bara intressant som vi och så teach det här möjligheten som kommer och vi hållande ja alltså det kan man säga det är ett grupp av möjligheter som det kommer och fyller intressen det alltså det här är inte bara stick samman av elektroföring alltså verkföring det är här är software här är elektron här är mekanik här är astrobiologer här är geologer så att alltså jag har onkan chans att värdera jag hittar i tecken på fototeologi nej jag kan hjälpa dem med att navigera tåle som matar gematingarna och bitcha till tåle och gör det möjligt för dig. Och jag kan så hjälpa dem att förtolka resultaten, men de må förtolka det ändliga resultatet om framatiken om detta kan vara något från, alltså vara från teologi. Det har vi inte bakgrund till. Alltså, nej. Men jag vill nöjd till att något som team om uppe till rätt fullständigt för att man fär samman om ett större projekt på sjön. Så jag tar nöklarna på det.
Jag halta alltså du ser alltså att det blir till att komma från någonskolan och helt nästan ut av mars. Det är viktigt att vi tar eller att det unga hör. Den här annars så vill spela något.
Jag hungrar jag cyklar nog och nu nämnde Brynhild till att här är ju något drönchur och gentor som är yngre som kunde komma till tilltaget men kanske en spurning som en liten drongrej vill jag finna svära är hur styr man en sån äkfärg uppe i mars från Jörnia?
Det är väldigt god spurningar och det är faktiskt rätt komplexa affärer. Hela tiden när vi köra röna kalibrera och allt det där och styra drone så fyra gånger allt en kommando till råvaren och en kommando åter. Och en kommandoen hon blir sänd via till helt stora antenner. Det är som har fotbollsbane också rätt. Här tror jag att Havn har gjort en i USA, Australien och mycket det syster någonstans i Europa har det stått fint. Det för jag får fototäckning och så kartospunkt att täckna det. Så man får en geodam kvant nu ska du lite masten upp och så ska du boja och då du just här så sänder en kommando nu livet ja. Och den kommandon får vi och så kan vi säga okej, nästa skritt. Till att börja vi har man liksom man skulle lyckas med lära grundva man kan gänga och man kan renna. Så här är det sån och till isen för att kött kunna finna av att hvis nu också inte ryckar så har vi spelat en highland där och få matingen den efter bara där första ryckar inte. Okej mat. Så där första tror jag mannen det kör allt på Mars daytime. Alltså en marsdag är en halv timme längre än en dag här hjörne. Så det är liksom Rutland i affära här man har notarbete. Och grunden till man hävt till till att det mest arbete vi då tar 4 gånger om dagen. De flesta talen riktigt har inte kamera i hava utan vid har blitzvis så det så gör ju något något. Som man som opererar som där i mars. Och så där så tror man lite ner så för man ivra ta mera science operations alltså ta forskningsmässiga har man mera jätla för efter forskningsresultaten och det har vi på dagliga basis som man sänder en stack och kommandoen i en sekvens tack den skulle göra det är ena och så kör en meter utfallda armen ut och för att ta på och stanna här och göra matingen där fallda åter och så sända all data till ett ateljörna. Och det är sån shift som kör som tar det där kvar för. Det är spännande på hver mars imot til hjørna. Minst til at hjørna og mars begge tvei i ringgras solna, men vi tar ikke akkurat det samme hastigheten rundt. Det teker 1 år for hjørna kommer rundt, så teker det 2 år for mars kommer rundt. Så det kan godt være kvarje sin suge og solna. Men i tjekknesnitt så teker det 20 minutter for signal fra hjørna og kommer fram til mars. Og så 20 minutter rett. Så det är inte så man sitter och bojar och okej ja alltså det nu har vi shit det har man inte skulle vara river shoulder till landingen och operations men allt team är skor ner till det absoluta minimum egentligen när corona och alltså I halt shower Nick Myron 24 folk lokalt och JBL i operations så att det resten av folken on call utifrån och vi såg sträckade som att man inte in där lokalt väl men allt är så det är automatiserat till den digital dömes så antingen gång det väl det lästen gång det inte så finner man att det man kan chans till att kontrollera att ta det händer det lendingen sekvensen det tog inte man tror jag något det men hvis jeg tenker 20 minutter for å få signal at det gjør om at også skal det så og vi skulle reagere på det så 20 minutter at træte men så det liksom lenter av det crasher av det til bøygen fram det til alt en atmosfære prosess ja, flere spørninger ikke alt at det
If there are no others, maybe I could ask a question.
Yeah.
And there are 2, but you can pick which one you prefer to answer first, I guess. And if there's time, maybe even answer both. So one is that you've spoken a lot about teams. And I can see that you're part of a very big team. You show the picture of yourself and your colleagues. And I guess for everything to work very well, and everything does need to work very well, that team also needs to work very well. So I wonder if you could maybe offer a few comments on how a team is encouraged to work very well to deliver those results. And I guess while I'm listening to you, I'm thinking, if I was in your shoes, that I would have some scary thoughts about how things might not work out in the way that you had hoped. And I wonder if maybe you might want to share some of your thoughts about, maybe some of those moments when you have had concerns about everything not working quite as well as you would have liked it to. Mm-hmm.
Yeah. I'll take the last one first. I think our bulk of work and where it really gets very, very busy is just before delivery of the instrument at the instrument level. When we deliver this hardware, the frame of the spacecraft is just waiting for us to assemble it, right? And we test everything at the instrument level. Then everything is or at this subcomponent level. Then it's tested at JPL at instrument level, and it's tested at JPL or at NASA at the rover level. So everything's tested at least 3 times. Because there are different configurations for everything, and you need to show that the spacecraft as a whole is working properly. And I think that where the phase where this whole rover was tested in the thermal chamber, that was my busiest period I've ever experienced, because there were so many. I had daily telecons of 2 hours with JPL just to talk about what happened and the data and the causes for it. JPL works like they put 100 people on the other side, and you have to answer all these questions that are coming from a lot of people and putting pressure on you to get it delivered, right? But at the same time, you're kind of a small team, and you also have the time, need to use the time to actually fix it, right? Instead of just talking about it, you need to figure it out. And that was very difficult to balance that. And you just wanted to, just calm down. We'll look at it, right? And spend your time wisely. But you also need to show that you're actually doing that work and putting the effort to it. So what I think after that period, we'd put in the process of doing the right test, just doing it in flight at both hot temperatures and at cold temperatures, and everything works fine with the setting that we chose. So that's very nice. But typically you have this, the unknown unknowns. If you don't know what to expect, if there's something that have I forgotten anything, right? That can be a scary thought. But that's why you kind of build a very elaborate test scheme. We have a phrase that says, test as you fly, fly as you test. That means that you always test your equipment the same way that you're intending to fly. And when you're in flight, you use the same scheme as you did for test. You don't wander off from that, because there are some elements. This is a big machine. There are a lot of things that you might not be aware of on the other side of the fence, that you can ripple to. If you have a specific behavior, it can ripple further onto the spacecraft or other instruments. And you don't want that. You want it to be a very controlled and foreseeable action and reaction of the spacecraft. So you're very. It's a very tight scheme, if I can say so. So I don't know. I think from what I'm aware of, I think I'm in the safe zone. But we'll see. I think for the calibration after this, the calibration effort in flight, we might see surprises. I don't know. I don't think so. We are well prepared, but you never know. And in terms of the teams, we need to trust each other. If there is, if something comes up that's not working properly, we need to make sure that I can trust you, that you will tell the rest of the team that something went wrong, or I dropped equipment on the floor. Whatever happens, we need to know so we can deal with it. That's extremely important. The whole production team, they are 5 to 8 people. They are assembling all the instruments here, soldering all the components. We have procedures for everything. Which component comes on first, what temperature you need to solder it on, and if the most we cannot stray away from that specific process or that specific manual, because we've been doing it for years exactly this way. And if you start doing it just slightly different, there might come up surprises that you did not think of. You know, the soldering did not work just exactly as well as you're used to, so it might be more fragile for all the thermal daily shifts that you have every day. So we need to trust each other very well and interact very well. We try to have quite a plain scheme, you know, organization, so we can just interact directly, and I don't need to go to the software lead in order to ask the guy who tested the software. I can just go straight to him. But I mean, there are limits to that. For a bigger organization than 40 people, it gets very difficult. So you have to have a matrix organization. But so far, I'm very fond of having a direct contact to everybody. And even now, 40 people, I don't, I don't always know what all the guys, that all the groups are doing all the time, but I have a very, very good idea, and I know who to go to when I need something. Does that answer it?
Thank you.
All right.
Yeah, I think we have time for one more. And Una?
Yeah.
Att jag spelar för en 5-6 år sedan så var det några som talade om i Føroya och arbets med erfaring vi kamerafolken som vi säger egna varje mastcam folkne. Och det är 6-7 år sedan kört långt Så kan du fortälja syndrom vad tid arbetar på nu som så i framtiden för att hända alltså framtida projekt som tid
Det kan jag absolut. Ett av dem här är faktiskt vi kunde inte bara spela på en häst. Vi var nødt til at sende neck proposals ut. Og det så det men här är flera missioner att ett av dem är så här Mars sample return. Vi har Eisenhower-tøkni innan formation flying, altså formationsflygning i rundene. Det kan synes det hvis du Top Gun-filmeren. Han har alltid en wingman som flyger beint utenfor, ja? Til formation flight. Han flyger beint vikvernørene. Og til akkurat det samme i rundene, bare med den tvers av litt av steg. Og da hender raketten fra Mars opp i orbit om Mars, og skal ha en sånn rendezvous, altså møtes vi i hinsatellitten som er i ringgras, så skal man ha automatiske prosesser og tål til at navigere mellom hver annan. Her er 20 minutter typisk til at signal kommer fram og kommer alltid og ta det krasjer så gjør det beina veien. Man hever ikke stunder til at det kontrollerer det for å gjøre det. Så det skal bli en automatisk prosess. Og det bruker vi kameratøkene til at navigere vi og simpelthen bare hitcher til innom rakettene og sørger hver ned og mate alle tøyene og så får man spekler igjen. Til en av dem og til synder fremalige men det er i utpåsfasen nu. Hva det andre så eisen en ESA-mission til formationsfløkene rundt om hjørnet og til faktisk at det er rett interessant at her bruker man typisk i det her teleskoper som er så stor at det er begrenset av volumen og masse som det kunne sende av med raketten. Hubble var så størst som det kunne være, men nu har man så gjort det at man har en sensor vid teleskopen og så en bom, eller altså en mast som er ganske 8 meter lengd, og så har man spekkel her ute til å fokusere røntgenstråler innan etter sensorene. Så det er så størst som det blir. Men hva nu hvis vi bare fjerne etter tårene og klipper det over og tager hver sånne ting lengt vekk fra kornøren, så får vi denne fokallengde, altså opp til 150 meter i runden, hvis vi bare flikker det og får det til en annan. Og det er meningen at det vi har snøret så er som misjonen at det gjør en stor studie av koronaen og solen, som man ser det mer tatt til at man får en virtuell fokallengde. Og det vi nok launcha innanfor halvt annet år også. og så det eisne tøkne til å landa ekfør av mars, eller av mannen, eller det kan gjøres at det kan være imenske mannen, eller asteroider, bare navigere i forhold til det. Så her er nok sånn imest at det tager Petra.
We maybe have time for just one more. If anyone is keen. We have one more.
Hva gjør det for at rutta opp i øtlen og rutten som reker rundt om åkken?
Det er en god spørning. Altså, det er faktisk et størst problem at hver for meg skjuter også i orbit, så er referring til resten til flytbare rute. Og vi togene vil det så brenne opp i atmosfæren, men det kan an på hatten og orbit, så kan det godt taka halvtrus år det kommer så lengt ned at det ikke fatter i atmosfæren. Og her er nekra missioner som er i on the drawing board om du vil. Men her er mitt forska i å gjøre navigasjon utan bruk av, altså det er eisende basert på formationsflukning egentlig, ja, men det er bare utan at man har nekra informasjon av hinnom rundt affæren. Så man vill bruka tøkne til å navigere vi, og så fengar jeg sier bare debris, kallar man det, altså skrotte garbage som ligger der. Og så bare taka det, og så gjør det sin fyr, skump ned etter, eller faktisk for ikke ned etter, men det er for atterur. Det er hvis du har sanka farten, så først du ned. Og så släpper man atter, og så får man selv opp i hastighet atter, og fengar det nesta. Man arbeider på at det har liksom et net som får liksom skyder ut og bare fengar det. Altså, her er nekko måter å gjøre det spon, sågar, altså, og det er et problem, tror at det er en risiko for hvis et objekt er for tatt på. De fleste årene har filmen Gravity til dømes, og det er akkurat det problemet. Og det er eisende problem for teleskopene her å gjøre det, at det er ljós for regning. Så at det skrottet som ligger her, tar vi belust av solene, så får vi ljós inn til store teleskopene, men det er ikke vi skulle sitte øye lyd ljós lengt fra galaksen. Så det er eisende ljós for regning, om du vil. Så her er hva skal man si, initiatives for at røyne at håndtere det sin bedre.
Well, thank you very much indeed, David. On behalf of the University of the Faroe Islands, Fróðskaparsetur, Føroya, on behalf of all of the people here today, both the people who are here with us in the room and also the people who are watching us streaming, both domestically and internationally, a very big thank you indeed. A wonderful presentation, delivered, I thought, really well to the audience in terms of making science and technology understandable and meaningful for people in their everyday lives. I'm sure that we'll all be watching the story of the Perseverance rover with great interest in the coming period and thinking of you every time it happens. We hope it won't be the last time. We'll have you presenting here in this building or in some of our other buildings. So before we retire to the foyer here, you can probably smell the smell of freshly baked pizza wafting into the room as we speak. So the university would like to invite you all to share some pizza and some soda or a glass of wine or whatever else there is there today with us. And before we finally go, I just ask you to put your hands together for a very warm vote of thanks for David. Thank you very much indeed.
Thank you for having me. Thank you.
Thank you very much indeed. Thank you. Fantastic.